All right, so now that we're back on track from our last video, which covered line integrals with scalar functions, basically functions that just kind of pop out numbers as values, we're going to kind of cover the topic of line integrals over vector fields, which, should translate pretty naturally from what we've been talking about in terms of line integrals that, happen over paths. Right, and the idea is that now we're still going to have the same idea where maybe we're calculating the total work done over some path C, but now instead of in the last video we had some function f of x y that represented something, and so we said that the integral of that function over some little bit of arc length was the line integral. Okay, it was adding up whatever that function represented over our curve C, and there's usually a C denoted here to indicate that we're talking about this path, so on and so forth. So that's the line integral we did last time. Now what we're going to have is we are going to have a vector field. And remember that this vector field, could represent wind, it could represent energy, it could represent force, it could represent a whole bunch of stuff. And you can imagine that the idea is that if we want to talk about, the line integral of this vector field f, right? The line integral, of f over c, right, over our path c, what might this give us, right? What real world thing does this do? And it shouldn't be too hard to think of. I mean, so imagine, let's say that this curve, let's say that c represents the path of a fly, okay, the path of a fly, and if f represents, the wind force, okay, wind force, at any point, let's say, let's keep this 2D, so on the xy plane. I drew this in 3D, but technically this is all happening in 2 dimensions without this axis here. And so if F is the wind force, then what are we calculating here when we're doing, and if we talk about the integral of the vector field F over C, well, this right here would be, well, last time we checked, if we do force, over like some small little distance, this right here is the physics concept of work. So this would be like the total work, or perhaps the total energy expended by the fly to, go from point A to point B on its little path. Okay. Now, hopefully you're paying very close attention and you notice that I have intentionally left this out. I didn't put ds here. Okay? I didn't put ds because when we talk about a vector field, okay, so maybe off to the side here, I'll write this. So when we talk about a vector field F is usually parameterized. Okay, I wish I could spell, but I'm an English major, not a math major. Actually, vice versa, I guess. F is usually parameterized, using t or some variable, and so is the path C, and so is C. Okay, so if you paid close attention to the video I released, talking about vector fields and how some vector fields, right, a basic vector field might just look like this. Let's say this is a 2D vector field. Maybe it gives us x plus y, and the second one is just y squared or something, right? That's a vector field. But if our path, say, is the top half of a circle, we might use the parameterization given by this vector function r to say that we're talking about let's say the top half of the unit circle, so given by x is equal to cosine of t and y is equal to sine of t, where t goes from 0 to pi, okay? And so this right here is a little bit different than just putting together a simple line integral of a scalar function, okay? It's a slight bit different, but it's not too bad, okay? So the difference here is that a vector field F consists of, well, just that. It consists of vectors, right? It consists of a bunch of vectors. And vectors, not only do they have a magnitude, a length, they have a direction, okay? And so too does our little path C, right? This path C that exists on our xy plane has a direction of travel. It's indicated by an arrow, right? In this case, right, our parameterization that I just made up out of thin air for the unit circle has an orientation, a positive orientation. It's counterclockwise and it goes from right to left, like so. And so how does this all pay attention, like add up and give us the line integral of f? Like, how do we come up with the formula? The idea is that we want to add up all of like the little tiny forces. So the amount of force, or the amount of our vector field F, going in the direction of what? What do we want it to be going in the direction of? Well, we want it to be going in the direction of our path C, right? We want, so remember, right? Okay, so the fly, right? The little fly, I don't even know how to draw a fly, but I will try, right? Let's say this is a fly and it's got some wings, right? Okay, this is, don't sue me, not an art major, okay? And it's flying along the path. It's going this way, okay? But the wind, there's a crosswind, it's blowing that way, and it's blowing this way, and it's blowing every which way that's indicated by all those little arrows on the screen, right? I want to know, I don't care about the amount of work or the amount of energy that the fly has to expend not going side to side. What I really care about is figuring out the total amount of energy that the fly will expend going in the exact direction of this particular path, okay? And so what that means is we need to figure out at every single one of these points, at every single point where there is a vector that exists on this curve, right? At every single one of those, notice how the vectors are not going, they're not all just facing in the direction of our path, right? There's, you know, some of them are facing backwards, some of them are facing forwards, right? I could make one here that's kind of going in the direction of our path. They go in a whole bunch of different directions. And if you watch the one of the first videos I did for week 5, where I reminded everybody what the dot product was. The dot product essentially is our way of determining how much of something, how much of one vector is going in the direction of another. And so you're going to see here that the dot product is going to make an appearance in our formula for a line integral. Okay, so if we're setting this up, right, if we're setting this up, you know, we're going to have an integral over our path C. What are we adding up? Well, whatever our vector field F represents, it could be wind, it could be energy, it could be heat, it could be whatever it is that we're talking about, okay, in the appropriate application. And now we need to indicate going in the direction of C, okay, going in the direction of C. But C has been parameterized by what? Well, C has been parameterized by our path R, right? R of t is the parameterization of our path C. So in other words, we want the amount of our vector field that's going in the direction of R over a very, you know, small, tiny little bit of R, because we're zooming in and saying that this path is really being parameterized by our R of t. And so we're need to do this calculation a bazillion times at a whole bunch of different points over a little tiny bit of R. So instead of a change in S, right? Instead of a small change in arc length, which is what we used for scalar functions, we're going to do a small change in our path, right? But this time, our path is described not by s, it's not just ds, it's not just good old-fashioned, c is not just y equals x squared, for instance. C has been given by our path r, right? We've parameterized it in some way. And so this right here, what I just came up with, this right here is a line integral of a vector field over some path c. Now, this looks a little bit weird, right now without much context, and it's true we need to do a little bit more with this, but I think I'm going to write down an example and then explain kind of what to do with the dr a little bit more specifically. So, for example, right, what might this look like? You might be given a problem that says, find the work, okay, find the work done by the force field. And you're like, force field, is this Star Trek? Yeah, we have force fields. We have like gravitational force fields, magnetic force fields, whole bunch of types. So find the work done by the force field given by the vector function f of x, y, or excuse me, vector field. And this vector field looks like this. Again, just kind of pulling it out of thin air. And so it's the work done by the force field in moving a particle, that's our fly, but the book likes to use particle, it doesn't like flies, along the quarter circle, given by r of t equals, we'll stick with our, looks like our unit circle here, cosine of t, sine of t, and we'll just let t go from 0 to pi over 2. We'll keep things simple for our quarter circle, okay? So that's what we're doing. Here's going to be a small little sketch of kind of our path. So we have a quarter circle. Now, just looking by this, because we've worked with this particular parameterization of the unit circle a lot, this is a positively oriented, maybe I'll, well, I don't think I can just draw a quarter circle, so I'll just do this. Right, this is a positively oriented path. It's the first quarter of our unit circle. And our vector field is doing some amount of work, okay? So that means, our vector field technically exists at every single point possible in 2D space, but we are more specifically interested in the force that's being exerted at every single point along this particular path of our particle, right? That's what we're really interested in. And so we can start setting up this integral by just kind of intuitively following what we have here. So we integral, maybe we kind of intuitively say, okay, we're given our bounds for t. We did something similar in the last video where we would put like t equals 0 here, and we'd put pi over 2 for the upper bound. We have our vector field, which is given by f of x, y, but again, per the last video, we know that we need to replace all those x's with cosine and all of those y's with sine. So maybe I'm going to put my vector field in here, but I'll have cosine squared of t, comma, cosine of t, sine of t. Okay, so that right there, this is just my vector field. This is f of x, y, but it is, but it has been parameterized, right? X has been parameterized in terms of t, and y has been parameterized in terms of t, because these are the values of x and y specifically along this path going that way of our quarter circle. Okay, now the weird thing that I promised to talk a little bit more about is what do we do with this dot dr, because we have everything in terms of t, 0, pi over 2 is in terms of t, our vector field is in terms of t. I don't even, like, what the heck does it mean to integrate this, a vector, like in this notation, what does that mean? And so what we're going to do really quick is just take a very brief deep dive into what does this mean, right? What does this whole, in the direction of our path, like what does that mean? Okay, what does that mean? So at this point in the video, if you're not very familiar with tangent vectors or the unit tangent vector of something, I would like you to pause the video and go watch some video or read in the textbook about unit tangent vectors, because that is exactly what I'm going to talk about right now. Okay, and so this whole in the direction of our path, how could we interpret this in a more meaningful way? Well, when we're talking about at a particular point on our path, going in the direction of our path, we are talking specifically about the unit tangent vector big T, right? In the textbook, it's big T. And the unit tangent vector is simply just the derivative of our path, r prime of t, but we have modified it, we have scaled it by its own length, right? Now, why does that give you a unit vector? Well, remember, because if I have any particular vector, and let's say that vector has length 5, but I want it to simply be a vector that just goes in a direction, I would divide it by 5. That way the vector has length 1, and we call that a unit vector. So the unit tangent vector, right, this whole idea of kind of going in the direction of our path, this right here, right, this right here represents the direction, okay, of our path at any time t. Okay, that's what that represents. Now, the last thing we need, right, because dr, right, it's a vector, and vectors have direction and magnitude. And so we've already figured out that I can replace dr, I can replace the direction part of it with this r prime of t divided by the magnitude of r prime of t. Now, the question, the last remaining thing is, okay, if that's the direction, then how do I get the magnitude of our path? Well, the magnitude of our path, that's just the length right here, and that is actually good old-fashioned ds, right? We know that when we cut this path into a whole bunch of little pieces, at any point, each one of those pieces has a width of ds, and so that's what we're going to stick with. We're going to put like a ds here. So this definition of what a line integral over a vector field is kind of comes to a head, and we can rewrite this of this particular form. It's of our vector field, it's of our vector field f in the direction, right, in the direction of our path. And this right here, the magnitude of r prime of t, right, that right there is the direction, and that is the length. So this right here is the same thing as dr. Now, if this seems a little bit strange, and you're like, what the heck is this? Well, let me do you one further and let your brain continue to melt a little more. ds, right, we still haven't solved our problem, which is that we're integrating something and our bounds are in terms of t, but hopefully remember from the last video that ds, we could rewrite it as the square root of dx dt squared plus dy dt quantity squared, and then keep a dt on the outside. Now here is the very, very interesting part. This right here, because we're talking about our path r, right? Our path is c, it's been parameterized by r. So what is this? What is this that I have just circled? Well, this is the same exact thing as the magnitude of r prime of t, right? That's what it is, right? If you think about it, if you take r, right? Let's take r, which is equal to something in terms of, x, right? X of t, and something in terms of y, right? Y of t, like so. And I take r prime, well, that's going to be dx dt and dy dt. And then, so what is the magnitude of this? What is the length of this vector? Well, you do that by Pythagorean theorem, right? You do this by using this little square root thing. So all of this to say, right, well, what are we doing? We're trying to figure out how to really understand this very simple formula that we very easily came up with, this notion of, you know, the amount of our vector field f going in the direction of our path r. We're trying to turn that dr into something we can actually work with, and we said, okay, well, it makes sense that in order to do, you know, dr as a vector, we need the magnitude, or excuse me, we need the direction of that vector, which is given by the unit tangent vector t. Oops, that's not, there we go, the unit tangent vector t. And then we also need a magnitude, which is given by ds. And we said that ds can be broken down into what I wrote there on the right, and that this, right, this bit right here is just the magnitude of r prime. So what does this do for our formula? This means that the line integral over a vector field is just as simple as saying it's the amount of our vector field f dot, now it's going to be r prime of t over the magnitude r prime of t. And then what does ds become? Well, ds just becomes magnitude of r prime of t dt. And as you can hopefully very readily see, these cancel out and just leave us with the actual workable formula of f dot r prime of t dt. Okay, and so this is really important. This is kind of like our workable formula. So you're like, why didn't you just give us this in the first place? Well, because the textbook, the textbook gives this formula and says, hey, look, doesn't this make sense that this is the line integral of the vector field f in the direction of our path? And I'm like, okay, sure. But this is the actual formula that we'll use to get solutions for problems. And so since we have a lot written down here, I'm going to erase a lot of this and revisit this problem that we are currently working with. And the problem that we're currently working with is that we're trying to find the work done by this vector field f it's moving a particle along this quarter circle. So our path has been given to us. Our path C is given by this. It's been parameterized in terms of r really nicely. And we started a setup at the top, which I'm going to kind of rewrite here. So we had t went from 0 to pi over 2. We had our vector field, which has been parameterized in terms of the x and the y's for our path. So we have cosine squared of t, comma cosine of t, sine of t, right? Very excellent. And now, right, so that's that part. So now all we're missing is the rest of this little formula. And so all we need to do is do the dot product with r prime of t. So what is r prime going to be? Well, let's see. The derivative of cosine, last time I checked, is negative sine of t. And the derivative of sine is going to be cosine of t. And we put a dt on the end here. Now, if you're wondering, is that it? Yeah, this is it. This right here is the setup for calculating this particular line integral, okay? And this line integral, what does it mean from an interpretive standpoint? It gives us the total work done by whatever this force field is, magnetic field, energy field, whatever it is, whatever application we've been given, and we're given a path, this is going to do it. This is going to calculate the total work done. And so how do we keep going with this? Well, the first thing that we're going to do is actually do the dot product, right? Because that's what we have. And remember, the dot product gives us just a single thingamabob to work with. So we're going to go piece by piece. So the first one's going to be negative sine of t times cosine squared of t. And then plus, And then the last one is going to become a sine of t times cosine squared of t. And apologize for switching things around. I just like to write sine first, so hope that doesn't bother many of you. And at this point, this is just solved, right? This, you can break it into two separate integrals. You can do u substitutions if you want, u substitution, and we can, this is very solvable, okay? Now, if the answer is positive, right, that means the total amount of work, the total amount of energy we've been expending is a positive number. That means we've been using energy. And if it's negative, that means we've been gaining energy, right? That means somehow we're absorbing the energy, and you can interpret that answer as you will. So I'm actually just going to leave it set up really nicely like so, to kind of to just kind of understand and underline the setup portion of this entire thing. So just to kind of recap, it turns out that the line integral of a vector field f over some path c, that formula is as simple as, well, there's our vector field f dot in the direction of our path, and this thing simplified a little bit, or rather was workable in the form f, and then we do the dot product of r prime of t dt. And I'll put this off to a side and then erase it in a second, but this should also kind of make sense, because what's r prime? R prime is dr dt dot dt, and what happens when you have this? You just cross out the dt's and it gets you back the dr that we had in the first place. So hopefully this formula kind of makes sense as to why it exists and why these are actually the same thing. And under it, I'm just going to remind you that, I did it earlier in the video, but I'd like to do it again. The line integral of a scalar function f, and I don't even need to put of xy because we're just doing 2D, over some path c. This is slightly different, and it's looks like so. Here's our f, but it's dot ds. And so this for us, if everything is in terms of x and y, was just f, and then we had, square root of 1 plus dy dx squared dx, that was like this. Or if it was in terms of t, this is actually just f multiplied by, it turns out that if this is all parameterized in terms of t, we can simplify this to just be magnitude r prime of t dt, which isn't so bad. And again, I just said that's because this is just the square root of dx dt squared plus dy dt squared, dt, okay, from our last video. So this is line integrals over vector fields. This is probably the most important thing. Really understanding these formulas is going to be really crucial for understanding how to set things up and how to think about these problems kind of going forward. So try to internalize that, try and be like, okay, this makes sense. Vector field going in the path of our curve, which is given by r, so f dot dr. And then, and so, right, this is a dot product. And then down here, this is just regular multiplication, because this is a scalar function down here, so multiplication. Okay, and it's just how much of our function is going in the direction of our path, or what is the value of our function, over this path. Now, there is one more relationship between line integrals over vector fields and line integrals over scalar fields. And so just to kind of show you something kind of nifty, so and this will play a bigger role next week, but a cool relationship between, line integrals of vector fields over a curve versus line integrals of a function over a curve is the following. Okay, so what I'm going to do is I'm just going to make a little setup here. So let's let f, let's introduce, say, a 3D vector field. So let's let f be equal to some 3D vector field. So it has a first component, which we usually call P, has a second component, which we usually call Q, has a third component, which guess what letter comes after Q? R, right? Let's let this, and let's say that R of t, little r of t, is going to be our parameterization of our path, okay? And so if we're doing a line integral of our vector field over our path, okay, it might look something like this. Okay, it would look like integral from, our starting point to our ending point. And then our vector field f would, of course, be parameterized in terms of r. And the way that we usually shorthand this is just f of r of t. And all that means is that, we're going to use whatever values for x, y, and z in for the p function. We're going to use whatever values of x, y, and z for the q function, and so on and so forth for the r component. Basically just plugging in all the appropriate parameterizations into our vector field. And so we're setting up our line integral, and then we, dot this into our r prime of t dt. And again, this is just right here. This is our dr from earlier. So what does this end up looking like? Well, this right here is the integral from a to b of, okay, so what does our vector field look like? Our vector field is, p, q, and r, right? Technically, they're all parameterized in terms of t. Okay, so it's p, q, and r. That's our vector field. And then dot, what's r prime look like? Well, r prime, since r prime is in terms of, we have x, y, and z, then the derivative of all those individually would just be dx dt, dy dt, and dc dt. And then we just have like a dt on the outside from this remaining one. Now, what if we actually do this dot product, what do we actually get? Well, check this out. If I do this, right, if I distribute in this dt to all of these, if I distribute that in first, I'm going to get, right, what am I going to get here? This last vector here just becomes dx, dy, dz. So when I do this dot product with the vector field, what am I going to get? Well, I just get the integral from a to b of p dx plus q dy plus r dz. I get this weird little formula right here. Okay, and this is going to play a little bit more of an interesting role later on. You can kind of think about this as indicating that the amount of our vector field going in the direction of our path is equivalent to like how much is going in the x direction plus how much is going in the y direction and plus how much of the z component is going in the z direction, right? And so maybe I'll try and give like a drawing that kind of gives an intuitive explanation for why this might be. Maybe I'll just do it in 2 dimensions though. Let's imagine that at this point here, our vector field is going there, okay? And our path is doing like this, okay? So this is our path C. And so what this is it's basically saying that the amount of this vector field that's actually going in the direction of C basically says, look, at this point, I can break down my vector field into like a y component. I can break it down into an x component. Likewise, with my curve C, I can break down my curve C technically on an infinitely small level into like some x components and into some y component. And it's basically saying that one other way of thinking about the amount of f, the amount of our of our vector field, the amount of our vector field going in the direction of C basically says, look, how much of the x component, how much of P is actually going in the direction of, our dx. And then how much of our y component, Q, is going in the direction of dy, right? How much of that is happening. And that should kind of make sense. And if you add up how much of the x component, how much of the y component, how much of the z components are all going in the appropriate directions, that should give you the amount of the vector field F going in the direction of your curve, aka the total work that you've done moving something along a particular path or whatever the application is. So this relationship is something that I just felt like showing you. It will rear its head a little bit more next week. So for now, you don't have to focus on it too much. I'd say the primary thing to focus on is this formula here and how we can turn it into its really useful formula, which is this one here, and maybe how it kind of compares to the good old-fashioned scalar formula like so. So check those out, practice them a little bit. If you'd like, in the files on Canvas, there is a special document there that kind of summarizes some of this. So check that out. It has some more information that we have not seen yet, so don't go too far if you don't want your brain to kind of become a melted pile of mush. But you can check it out. It kind of formalizes some of this and organizes it for you, so if you're doing your homework, you can kind of use that sheet to kind of help you out. So hopefully this is kind of interesting and it kind of makes some intuitive sense. The formula is very simple. It's very simple to do problems with. It's very simple to set up, but really understanding the ideas behind why these formulas exist and why they are the way they are will really make what's coming up in the next couple weeks very, very manageable. So I strongly recommend watching over the parts of the video again that really talk about the intuition between understanding this formula, understanding this set of formulas, and all that good stuff. And if you've got that, then you'll be ready for the next ones.